March 24th, 1944, 10:30 p.m. Stalag Luft III, prisoner of war camp, Nazi-occupied Poland. 336 feet underground, Flight Lieutenant Robert McBride crawled through absolute darkness. The tunnel was barely 2 feet square. Sandy walls pressed against his shoulders. The air tasted like metal and exhaustion. But here's what makes no sense. The Germans had designed this camp to be escape-proof. They'd planted seismograph microphones every few yards around the perimeter to detect digging sounds. They'd built the barracks on stilts so guards could see underneath. They'd even chosen this location specifically because its bright yellow sandy soil would be impossible to hide. Yet somehow, 600 Allied officers had just spent 11 months engineering 3 separate tunnel systems 30 feet beneath those microphones. Tonight, 76 men would crawl to freedom through a passage that defied every principle of Nazi security. The question isn't whether they escaped, it's how they solved problems that should have been impossible.
Stalag Luft III wasn't chosen by accident. When the Luftwaffe opened this camp in March 1942, they selected a location 100 miles southeast of Berlin for one specific reason. The soil composition made tunneling a nightmare. The entire area sat on deep beds of bright yellow sand that contrasted sharply with the gray topsoil visible throughout the compound. This created what German engineers called the yellow problem. Any tunnel dug more than 3 feet down would produce distinctive yellow sand that stood out like a beacon against the compound's gray surface. Dispose of even a handful, and guards would immediately spot the color difference. But the soil nightmare went deeper. Unlike clay or packed earth, this sandy substrate had zero structural integrity. Mining engineers classify such soil as Class 4, the most unstable category. Without constant reinforcement, tunnels would collapse within hours. The sand behaved almost like liquid, flowing and shifting with any vibration or disturbance. Squadron leader Roger Bushell, a South African RAF officer with a law degree, understood this challenge immediately. Captured in 1940, he'd already attempted multiple escapes from other camps. When he arrived at Stalag Luft III in October 1942, he assessed the situation with brutal honesty. "Gentlemen," he told the assembled prisoners in Hut 104, "the Germans think they've built an escape-proof camp. They're wrong, but we won't beat them with individual attempts. We need industrial-scale engineering." Bushell proposed something audacious: simultaneous construction of 3 tunnels designated Tom, Dick, and Harry. Each would be 30 feet deep to bypass the seismograph microphones planted around the camp perimeter. Each would stretch over 300 feet to reach the forest beyond the wire. The German defenses seemed insurmountable. Beyond the yellow sand problem, the camp featured double perimeter fences topped with barbed wire, guard towers positioned every 150 feet, and those seismograph microphones calibrated to detect footsteps from 30 feet away. But what the Germans didn't account for was one critical factor.
Among the 10,000 prisoners at Stalag Luft III was a 24-year-old Canadian officer named Wally Flutie. Before the war, Flutie had worked as a mucker, an underground miner in the gold mines of Kirkland Lake, Ontario. He'd spent years in cramped shafts hundreds of feet below the surface, learning exactly how to keep unstable rock from crushing him. Bushell appointed Flutie as chief tunnel engineer. It was the most important decision of the entire operation. Flutie immediately recognized that traditional tunneling approaches would fail. The yellow sand required constant shoring with wooden supports, but those supports had to be installed differently than in hard rock mines. Where rock allowed vertical supports every 5 feet, this sand demanded horizontal bracing every 18 inches. "Think of it like building a ship inside a bottle," Flutie explained to his team of diggers. "Every piece has to be precisely cut, precisely placed. One miscalculation and the entire section collapses." The engineering specifications Flutie developed were remarkably sophisticated. Each tunnel would measure exactly 2 feet square in cross-section, large enough for a man to crawl through, small enough to minimize excavation volume. At the base of each entrance shaft, 30 feet down, they'd construct a workshop chamber large enough for 3 men to work simultaneously. These chambers would be 40 inches high and 6 feet square. Every 100 feet along each tunnel's length, Flutie planned halfway houses, slightly enlarged chambers where exhausted diggers could rest and where tools could be staged. The tunnels would include functional air circulation systems, electric lighting, and an underground railway for sand removal. The biggest challenge? Those wooden supports. Flutie calculated that each tunnel would require approximately 1,400 individual wooden boards, each cut to precise dimensions and interlocked to create continuous structural integrity. The wood had to come from somewhere the Germans wouldn't notice, but they had already solved that problem before construction even began.
Between October 1942 and April 1943, a systematic operation unfolded across Stalag Luft III's North Compound. Prisoners carefully dismantled their bunk beds, removing individual boards. They disassembled tables and chairs. They broke down benches and shelving units. The Germans noticed, of course, but when asked, prisoners complained that the furniture was uncomfortable and they preferred sleeping on the floor. Guards shrugged. Crazy British flyers. What the Germans didn't see was the precise inventory management happening in Hut 104. A complete materials manifest was maintained showing exactly what had been acquired. 90 boards from bunk beds, 62 tables, 34 chairs, 76 benches, and thousands of smaller wooden items. Each piece was cataloged by size and stored in secret compartments built into the hut's double walls. But wooden boards were only the beginning. The tunnels required an entire ecosystem of engineering solutions. For lighting, prisoners stole electrical wire during visits to the camp workshop, smuggling it back in their clothing. They fashioned light fixtures from empty food tins, using fat from their meals as a primitive insulation material. The bulbs came from the barracks themselves, stolen in the night and reported as burnt out the next morning. The ventilation system presented the most elegant engineering solution of the entire operation. Red Cross parcels arrived regularly containing Klim powdered milk in sturdy metal tins approximately 4 inches in diameter. Prisoners removed both ends of these tins, creating metal tubes. By fitting these tubes together end to end, they constructed ventilation ducts that could snake hundreds of feet through the tunnel. But a duct is useless without air pressure. A prisoner named Bob Nelson, who'd been an engineering student before the war, designed an ingenious bellows system using canvas kit bags, wooden valves whittled from bedboards, and a rocking handle mechanism. One man working this pump could force fresh air through the entire duct system, providing breathable atmosphere even at the far end of a 300-foot tunnel. The underground railway system showed similar ingenuity. Small wooden trolleys were constructed, measuring approximately 18 inches square, with wheels carved from bedboards and axles fashioned from stolen metal rods. These trolleys ran on wooden rails laid along the tunnel floor. A rope system connected them, allowing a hauler stationed at the bottom of the entrance shaft to pull the trolley back and forth. One prisoner would dig, filling the trolley with sand. When full, he'd tug the rope twice. The hauler would pull the trolley back to the shaft, where the sand would be transferred to cloth bags for disposal. The empty trolley would return, and digging would resume. This system could move approximately 1 ton of sand every 12 hours. the minimum rate required to complete a 300-foot tunnel in 11 months. But moving sand underground was only half the problem. The real challenge was what happened when that sand reached the surface.
Remember that yellow sand problem? Every cubic foot of tunnel excavated 30 feet down produced bright yellow material that would immediately betray the operation. The total volume was staggering. Each tunnel would displace approximately 100 tons of sand over its complete length. 100 tons of bright yellow evidence. Squadron leader Roger Bushell assigned Flight Lieutenant Peter Fanshawe to solve this engineering nightmare. Fanshaw's solution demonstrated the kind of creative problem-solving that defined the entire operation. He developed what became known as the penguin system. Long cloth bags were sewn from torn-up long underwear, each measuring about 2 inches wide and 2 feet long. These bags were filled with yellow sand from the tunnels and fitted with a drawstring at the top. A prisoner acting as a penguin would tie these bags inside his trouser legs, securing them at his waist beneath his jacket. Walking normally, or as normally as possible with 2 bags of sand strapped to your legs, the penguin would move to a designated dispersal area. By pulling a string attached to the bottom of each bag, he could release a steady trickle of yellow sand as he walked. The sand would fall down through his trouser legs and disperse on the ground. Other prisoners would then shuffle through the area, scuffing the yellow sand into the gray topsoil with their feet, mixing the colors until the yellow became invisible. The system required extraordinary coordination. At peak operation, 140 penguins moved simultaneously through the compound, each depositing approximately 5 pounds of sand per trip. They walked predetermined routes, timing their movements to avoid suspicious patterns. Security men kept watch for guards, signaling penguins to stop dispersing sand if a patrol approached. But some areas of the compound were too closely watched for penguin operations. For these yellow sand surpluses, an alternative solution emerged. Tunnel Dick was converted into a storage facility. Rather than extending toward the perimeter wire, Dick became a massive underground chamber where tons of excess sand from Tom and Harry could be hidden indefinitely. The engineering coordination required to manage 3 separate tunnel systems, each with different functions, reveals the sophistication of the operation. Tom started from Hut 123 and extended westward. Harry began in Hut 104 and pushed north toward the forest. Dick, from Hut 122, went west initially, but then transformed into the sand storage depot. Each tunnel had dedicated teams of diggers, haulers, engineers, and dispersal personnel. By early September 1943, Tom had reached 260 feet and was approaching the tree line beyond the wire. Success seemed imminent. Then everything collapsed. September 8, 1943. A German guard on routine patrol noticed something strange near Hut 123. The ground had subsided slightly, barely noticeable, but enough to trigger suspicion. Within hours, German ferrets, security officers specializing in escape detection, had discovered Tunnel Tom. The Germans were stunned. The vertical shaft descended 30 feet. The horizontal tunnel stretched 260 feet, equipped with electric lights, ventilation ducts, and a functional railway system. Wooden shoring lined every inch. It was engineering that rivaled professional mining operations. Camp Commandant Friedrich Wilhelm von Lindaner-Wildau photographed everything. He sent detailed reports to Berlin highlighting the sophistication of the Allied engineering. He then ordered the tunnel filled with sewage to prevent reuse. For Roger Bushell, the loss of Tom was devastating but not fatal. Dick had already been converted to sand storage. That left Harry, the tunnel departing from Hut 104 toward the northern forest. "We put everything into Harry now," Bushell announced. "No distractions, no individual escapes, industrial focus." Wally Flutie intensified the engineering specifications.
Harry would incorporate every lesson learned from Tom. The wooden shoring was reinforced with interlocking joints that distributed weight more evenly. The ventilation system was expanded with additional Klim tin duct sections. The underground railway received upgraded trolleys with better wheel alignment. Work crews were reorganized. Each shift included one digger at the tunnel face, one man operating the air pump, one hauler managing the railway system, and multiple penguins above ground dispersing sand. Security teams watched for German patrols, while trapdoor specialists perfected the entrance concealment. The entrance to Harry was hidden beneath a heating stove in Hut 104. The stove sat on a metal frame that could be lifted by 4 men. Beneath it, a trapdoor opened into the vertical shaft. When closed, the trapdoor supported the stove's weight and was completely invisible. By March 1944, Harry had reached 336 feet, breaking the surface just beyond the camp's northern perimeter fence. But Wally Flutie never saw it completed. In January 1944, he was transferred to another camp as punishment for his known involvement in escape activities. Before he left, he briefed his replacement on every technical detail of the tunnel's construction. "Keep the air pumps running consistently," Flutie emphasized. "If the flow stops for more than 10 minutes, carbon dioxide accumulates at the tunnel face. Men have passed out down there." On the night of March 24th, 76 men prepared to crawl through Harry to freedom. They'd assembled civilian clothing, forged identification papers, and detailed maps. The tunnel represented 11 months of engineering brilliance, solving problems that should have been impossible. What they didn't know was that the tunnel had one final surprise.
10:15 p.m., March 24th, 1944. In Hut 104, Squadron Leader Roger Bushell lifted the heating stove aside. 4 men pulled up the trapdoor. The vertical shaft dropped 30 feet into darkness. A wooden ladder made from bedboards descended into the black. The first escapee, a flight lieutenant whose German was flawless, climbed down. At the shaft bottom, he crawled into the horizontal tunnel. The journey through 336 feet of 2-foot square passage would take approximately 20 minutes of steady crawling. The escape plan called for 1 man every 60 seconds, a rate that would allow all 220 prepared escapees to exit before dawn. The engineering seemed perfect, but when the first man reached the exit shaft and pushed up through the final trapdoor, he discovered a catastrophic miscalculation. The tunnel was 30 feet short. Instead of emerging in the forest's protective darkness, the exit lay in open ground with clear sight lines to the nearest guard tower. A miscalculation in surveying had shortened the tunnel's effective length. Every escapee would need to lie in the open, wait for the guard's attention to shift, then sprint for the tree line. The escape rate immediately dropped from 1 man per minute to 1 man every 10 minutes. Throughout the night, escapees crawled through the tunnel, emerged into the cold March air, and ran for the trees. By 4:30 a.m., 76 men had escaped. The 77th, emerging from the exit hole, was spotted by a guard. Sirens wailed. Lights flooded the compound. German soldiers poured into the camp, racing toward Hut 104. Inside the tunnel, men still waited to escape. As guards stormed the hut, those underground had to make an agonizing choice: crawl forward into certain capture or retreat back to the entrance shaft. Most chose to retreat, backing through 300 feet of cramped darkness. The German investigation revealed the full scope of what the prisoners had accomplished. Tunnel Harry measured 336 feet in length and 30 feet in depth. It contained 4,000 individual wooden boards assembled into continuous structural shoring. The ventilation system included approximately 1,400 Klim tin sections, totaling over 900 feet of ducting. The electric lighting system featured dozens of stolen bulbs powered by tapped electrical wires.
The underground railway included functional trolleys, wooden rails, and a rope and pulley system. 100 tons of bright yellow sand had been dispersed across the compound without detection. The entire operation had involved 600 prisoners working in coordinated shifts for 11 months. From a pure engineering standpoint, it remains one of the most sophisticated escape operations in military history. But the human cost was devastating.
Of the 76 escapees, 73 were recaptured within 2 weeks. Only 3 reached Allied territory: 2 Norwegian pilots who stowed away on a freighter to Sweden, and a Dutch pilot who reached Gibraltar. Adolf Hitler, enraged by the escape, personally ordered an unprecedented action. 50 of the recaptured officers, including Roger Bushell, were executed by the Gestapo. The murders violated the Geneva Convention and constituted a war crime that would be prosecuted after the war. The engineering brilliance of the tunnel system contrasted horrifically with the tragedy of the aftermath. But the technical innovations developed at Stalag Luft III outlived the war itself. The principles pioneered by Wally Flutie and his team influenced post-war mining safety regulations, particularly regarding ventilation and unstable soil conditions. The improvised railway system demonstrated efficient material transport in confined spaces, concepts later applied in underground construction projects. In 2011, archaeologists using ground-penetrating radar rediscovered Tunnel Harry beneath the former campsite. They found the wooden shoring still intact, the Klim tin ventilation ducts still in working order, and even some of the wooden trolley wheels preserved in the sand. Modern engineers who examined the tunnel were astounded by its sophistication. Dr. Hugh Hunt from Cambridge University's engineering department participated in a documentary where modern RAF officers attempted to replicate the tunnel construction using period-accurate tools and materials. "We struggled with every aspect," Hunt admitted, "and we had the benefit of modern knowledge, proper nutrition, and no time pressure." What they accomplished with improvised tools while under constant guard surveillance remains almost incomprehensible from an engineering standpoint. The trapdoor beneath the stove, the interlocking wooden shoring, the Klim tin ventilation system, the underground railway, each innovation solved a specific technical problem that professional engineers would find challenging even today.
Today, the site of Stalag Luft III operates as a museum. Visitors can see replicas of the tunnel systems, the improvised tools, and the wooden shoring techniques. The museum displays actual artifacts recovered during archaeological excavations. Klim tins still connected in ventilation chains, wooden boards with prisoner-carved joint connections, and even fragments of the trolley railway. But the real legacy isn't preserved in museums. It's embedded in how we approach engineering problems when resources are limited. The prisoners at Stalag Luft III faced constraints that seemed absolute: unstable soil, detection systems, limited materials, constant surveillance. They solved each problem not through brute force, but through creative application of fundamental engineering principles. Wally Flutie didn't have hydraulic shoring equipment, so he developed interlocking wooden joints that distributed weight through friction. The ventilation team didn't have industrial fans, so they created a bellows system using canvas and one-way valves. The railway builders didn't have steel rails, so they carved wooden tracks and wheels with tolerances precise enough for functional operation. Every piece of the tunnel system answered a specific technical question. How do you shore up unstable sand? How do you ventilate a 300-foot tunnel? How do you dispose of 100 tons of distinctively colored soil? How do you conceal a trap door supporting a heating stove's weight? The answers they developed through engineering ingenuity, systematic problem-solving, and relentless testing represent human creativity at its finest. 600 prisoners, 11 months, 3 tunnels, 100 tons of sand, 30 feet down, 336 feet out, all with spoons, bedboards, and powdered milk tins. If you found this technical breakdown fascinating, make sure you subscribe. We explore engineering challenges throughout military history, the problems soldiers and prisoners solved when failure meant death and success meant freedom. Because the question was never whether they could dig a tunnel. The question was always, how do you engineer the impossible?